Hello everyone, today we will discuss about generator and parity check metrics for NK cyclic codes. In the last class we discussed about the parity check matrix h of x. We know that h of x is a polynomial of degree k. Right. We know that both generator polynomial g of x and parity check polynomial h of x are factors of x raised to n plus 1. That means if you divide x raised to n plus 1 by g of x, the remainder will be 0 and quotient will be h of x. Or similarly, if you divide x raised to n plus 1 by h of x, the remainder will be 0 and the quotient will be g of x. Generally, we can write it as g of x into h of x equal to 0 modulo x raised to n plus 1. Okay. In the case of 7-4 cyclic code, we know that the generator polynomial and parity check polynomial are factors of x raised to 7 plus 1, right? So in the case of 7-4 cyclic code, x raised to 7 plus 1 can be written as x plus 1 into x cube plus x plus 1 into x cube plus x square plus 1. So if we select g of x, so that means in the case of 7-4 cyclic code, two generator polynomials are possible. So only constraint is the generator polynomial should be of degree 3. The degree of g of x should be n minus k. So in the case of 7-4 it is 7 minus 4, that is 3. So we can see that there are two polynomials of degree 3. So therefore two generator polynomials are possible in the case of 7-4 cyclic code. So if we select g of x equal to x cube plus x plus 1, then obviously what about h of x? Then h of x equal to x plus 1 into x cube plus x square plus 1. So this will be equal to, so if you multiply, we will get it as x raised to 4 plus x cube plus x cube plus x square plus 1. So x cube cancel. So you will get it as x raised to 4 plus x square plus x plus 1. So this already we discussed in the last class. Right. Similarly, if g of x is chosen as x cube plus x square plus 1, then h of x will be equal to x plus 1 into x cube plus x plus 1. So this will be equal to x raised to 4 plus x square plus x cube plus x plus 1. So this will be equal to x raised to 4 plus x cube plus x square plus 1. So if generator polynomial is selected as x cube plus x square plus 1, then h of x will be x raised to 4 plus x cube plus x square plus 1. Today we will construct the generator matrix and parity check matrix for NK cyclic code. So first of all we will construct the G matrix for an NK cyclic code. So to construct the generator matrix of dimension k by n, so we know that the dimension of G matrix is k by n, right? So we will consider the generator polynomial g of x and k minus 1 cyclic shifted version of g of x. Now in the case of G matrix, we know that the generator matrix has k rows and n columns. Now the first row will be the g of x. Second row will be the cyclic shifted version of g of x, which is equivalent to x into g of x. Third row will be the cyclic shifted version of x into g of x, or 2 cyclic shifted version of g of x, which is equivalent to x square into g of x. In this, if you proceed in this way, the last row will be x raised to k minus 1 g of x. That is k minus 1 cyclic shifted version of g of x. So this is the generator matrix for nk cyclic code. So we will consider an example. Consider the case of 7,4 cyclic code. G matrix for 7,4 cyclic code. So assume that g of x is x cube plus x plus 1. So we can see that the generator matrix has 4 rows and 7 columns, right? Because since the dimension of G matrix is 4 by 7. Now what will be the first row? What will be the first row? The first row will be the coefficients of the generator polynomial. So what are the coefficients? We will start from this term onwards. That is 1, 1, x, the coefficient of x square is 0, 0, and coefficient of x cube is 1. Now how many columns are there? There are 7 columns. So rest of the elements are filled with 0. Now how? So this will be g of x, or coefficients of g of x. Now how will you complete the second row? The second row will be the one cyclic shifted version of the first row, or g of x, which is equivalent to x into g of x. Now what is x into g of x? X into x cube plus x plus 1, that is x raised to 4 plus x square plus x. So if you write the coefficient, now the coefficient of first term will be 0, then 1, coefficient of x square is again 1, coefficient of x cube is 0, then again 1, 0, 0. So I will write the coefficient like this: 1, x, x square, x cube, x raised to 4, x raised to 5, x raised to 6. Now what about, how will you write the third row? Third row will be x square into g of x, which is equivalent to what? 2 times cyclic shifted version of the first row, or 2 times cyclic shifted version of g of x. So these 2 zeros will come here. So if you shift 2 times in this direction, so you will get it as 0, 0, 1, 1, 0, 1, 0. Now, so or we can write it as, what is x square into g of x? X square into g of x will be x raised to 5 plus x cube plus x square. So x square, x cube, then x raised to 5. Now how will you complete the fourth row? Fourth row will be 3 cyclic shifted version of g of x, or which is equivalent to x cube g of x. What is x cube g of x? It is x raised to 6 plus x raised to 4 plus x cube. So 1, 1, 0, 1. Rest of the elements are 0. Or 3 cyclic shifted version of g of x. So this will be the generator matrix for 7,4 cyclic code. But we can see that the generator matrix obtained is not in systematic form. We know that the general format of G matrix is I, P, where I is the identity matrix and P is the parity submatrix. So you can't identify the identity matrix here. So by doing some row operations, you can convert this generator matrix to systematic form. Now, what are the operations to be done? So I am designating each row as, say, this is R1, R2, R3 and R4. Okay. So our aim is we need to keep these two elements are 0, right? So the operation you can do is R1 equal to R1 plus R2 plus R3. R1 equal to R1 plus R2 plus R3. Then G can be written as, for what will be the first row becomes R1 equal to R1 plus R2 plus R3. So you can see that, so this one remains unchanged, 1. Then there are even number of ones here and here, also here. So it will be 0, 0, 0, 1, 1, 0. Now R2 equal to R2 plus R3 plus R4. That is 0, 1, 0, 0, 0, 1, 1. Okay. Now R3 equal to R3 plus R4. That is 0, 0, 1, 0, 1, 1, 1. And R4 equal to R4 itself, no problem. 0, 0, 0, 1, 1, 0, 1. So this is the G matrix in systematic form. So you can identify as I, P. So this is the generated matrix obtained, and these are the various operations we applied. That is R1 equal to R1 plus R2 plus R3, R2 equal to R2 plus R3 plus R4, R3 equal to R3 plus R4, and R4 equal to R4 itself. Okay. Now how will you construct the H matrix? We know that H equal to, what is the format of H if G equal to IP? H will be equal to P transpose I. Right. So this will be equal to P transpose 1 0 1 1 1 1 1 0 0 1 1 1. Now complete rest of the elements with the identity matrix 1 0 0 0 1 0 0 0 1. So this is the H matrix. Now we will construct H matrix from the parity check polynomial. So let the parity check polynomial h of x is x raised to 4 plus x square plus x plus 1. Now what is the dimension of H matrix? We know that dimension of H matrix is n minus k by n. So in the case of 7-4 cyclic code, the dimension of H matrix is 3 by 7. There are 3 rows and 7 columns. Now how will you construct the first row of H matrix? So we know that h of x is x raised to 4 plus x square plus x plus 1. Now step 1 is replace x by x inverse. H of x is converted to h of x inverse. So that will be equal to x raised to minus 4 plus x raised to minus 2 plus x raised to minus 1 plus 1. That is replace x by 1 by x. That's all. Now the first row of H matrix is constructed by providing 4 cyclic shift to H inverse, which is equivalent to x raised to 4 H inverse. So this will be equal to 1 plus x square plus x cube plus x raised to 4. Right. Now how many rows are present in H matrix? 3 rows. Now what will be the second row? Second row of H matrix will be x raised to 5 into H inverse. So that will be equal to x plus x cube plus x raised to 4 plus x raised to 5. Now third row will be x raised to 6 H inverse. That is equal to x square plus x raised to 4 plus x raised to 5 plus x raised to 6. So which is equivalent to one cyclic shifted version of this quantity, and this the third row will be the two cyclic shifted version of the first row. That's all. So h equal to, so I'll give it as 1 x square x cube x raised to 4 x raised to 5 x raised to 6. So 1 0 1 1 1 0 0. Second row will be 1 1 1 1 0 0 0. Third row will be 1 1 1 1. So this is the H matrix, and we can see that H matrix is not in the systematic form. Now we need to convert the H matrix in the systematic form. So for that I am designating this as R1, R2, R3. Now what is the format of H? H will be equal to P transpose I. Right, if G equal to IP. So we can see that the first row is okay. We can separate it as P and I. Right. So first row remains unchanged. 1 0 1 1 1 0 0. Right. Now this is R1. What is R2? R2 equal to R1 plus R2. R2 equal to R1 plus R2. That is 1 1 1 0 0 1 0. Similarly, R3 equal to R3 plus R2. So 0 1 1 1 0 0 1. So here we can see that this is in the systematic form, that is, this is P transpose and this is I. See, this is the matrix we already derived from the G matrix. H matrix already derived from the G matrix. So see, both are same. So in this way, we can construct the generator matrix and parity check matrix from generator polynomial and parity check polynomial. Thank you. So in this way, we can construct our G matrix from H matrix as G equal to IP, right? So this is P transpose. So now P is 1 1 0 0 1 1 1 1 1 1 0 1, and rest of it is complete with IMT matrix 0 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So comfortably we can derive G matrix from H matrix. Thank you.